Alright folks, so in this video we're going to look at derivatives and rates of change, and really it's very much an introduction to the derivative. So just as a reminder, when we first start talking about some of these calculus ideas, our motivating example was looking at tangent lines, trying to approximate those. We did that using secant lines. So just a reminder, the slope of the secant line through these 2 points, A, f of A, and B, f of B, well, it's just your usual slope calculation when you have 2 points. So nothing new there. The difference of the function value divided by the difference of the input values. Now the tangent line, before we talked about just making approximations. Now we can actually talk about making an exact computation. So the tangent line at a point is the line through the point with this slope. Now I'm using m sub sec, so secant there. The secant slope and tangent slope. Maybe not a common notation, but just for now to make it clear what it is we're talking about. So it looks kind of similar in terms of a slope calculation, but we've got this limit part of it as well. And like we've said before, limits are what make calculus work, what makes calculus happen. So if that limit exists, and we spent a lot of time talking about computing limits and so on, then that's what that slope of that tangent line will be. Another way of computing it, so basically the idea with this first one is you're seeing what happens as x gets closer and closer to a. So that closer and closer business that we've talked about is described mathematically using limits. So gets closer and closer and closer. Now we can't do a direct substitution and just plug in a for x because we get 0 over 0. So that's where it gets kind of interesting, and we've got to use some of the techniques and tools that we've learned for computing limits. If you let h equal x minus a, just change the name of x minus a to h, then really you're looking at the limit as h goes to 0 of this quotient, sometimes called the difference quotient. Now the way to think of h is think of it as the difference between your point in question A and the second point, whether it's x or whatever, but it's that width as that shrinks to 0. That's the idea. Now that limit, using either description, defines, so actually our definition of the derivative of a function at that point A. So we use this notation. When we talk about the derivative as a function, we'll have more notations, but for now this is the only one we'll really use. And we read this as f prime of A. So a little bit more formally, slash just a reminder, the derivative at a point f prime of A is the limit as x approaches A of f of x minus f of A over x minus A. Or equivalently, the limit as h approaches 0 of f of a plus h minus f of a all over h. So again, in terms of our motivating application, where we first started all our calculus topics, the derivative of a function at a point gives us the slope of the tangent line. Remember our motivating idea or example was we wanted to find a description of the tangent line. What you need for a line is a point and the slope, and the point would be given to us. So it all broke down to basically finding the slope of that line. And we do that with the derivative. So for an example, let's find an equation of the tangent line to the curve. F of x equals negative x squared plus f of x plus 4x, minus 2 at x equals 1. So what we're thinking of is the tangent line to that point. And the way we had done that before was, there's a secant line, there's a secant line, there's a secant line, there's a secant line. We get that better and better approximation, and the one that we want is going to be looking like something like that. We don't have to do this approximation business anymore because we've got this tool, this derivative. So that's what we want to do. We need compute f prime of 1 for the slope of the tangent. All right, so f prime of 1 is the limit. And we'll think about how we want to do this. Let's say as x approaches 1, of f of x minus f of 1 over x minus 1. And so that's negative x squared plus 4x minus 2. That's the f of x part. Minus f of 1 is going to be negative 1 plus 4 minus 2, which equals 1. So we've got 1 there. X minus 1. So this is negative x squared plus 4x. Now it's minus 3 over x minus 1. And I can factor that numerator as let's see, what would it be? How about x minus 1 times x minus 3? And so using the cancellation property, those x minus 1 common factors will cancel, and so it really is the same as the limit as x approaches 1 of negative quantity x minus 3. That's a linear function and polynomial. We'll do a direct substitution. So kind of crammed for space here because I'm squeezing in an example, but f prime of 1 equals 2. So on the next slide, we've got what that function what that tangent line looks like, and from before we saw f prime of 1 equals 2, and the point on the curve, the point on the tangent line, well, it's at x equals 1, and f of 1, we already said, was 1. And so the line y minus 1 equals 2 times x minus 1. That's our point slope form, or if you like, in slope intercept, it would be like this. And that's a description of that tangent line. Again, 2 is the slope of the tangent line at that point x equals 1, where x equals 1. All right, so I did this calculation using this description. All right, it's kind of messy there, but that's how it goes. Our other motivating application was velocity. So just as a reminder there, if f of t is the position function of an object at time t, the derivative at time a is the velocity at that time. And I said f of t here. You'll see in the problems that we're looking at, oftentimes they use s for position. And in fact, I've done that in an example here. So if a ball is thrown upward with an initial velocity of 36 feet per second, its height after t seconds is s of t. It's given by s of t equals 36t minus 16t squared, and that's measured in feet. So we want to find the velocity 2 seconds after the ball is thrown. What that means is we want to find the rate of change of position, the instantaneous rate of change, which is the velocity. So we want to find s prime of 2. All right? And so the way I'm going to do that Now, jumping back here real quick, I used this definition for the first time I computed a derivative. Let me try this one now. They are equivalent. So I'm going to say the limit as h approaches 0 of s of 2 plus h minus s of 2 all over h. All right, so s of 2 plus h is 36, 2 plus h minus 16, 2 plus h squared. All that minus what's s of 2? So that's 72 minus, looks like 64, so I think 8. All over h. And so we've got 72 plus 36h minus, now we'll do a little bit of scratch work here. So I've got minus 16 times 2 plus h squared, so minus 64, from the minus 16 times that, minus 64h, minus 16h squared, minus 8. All that over h. Alright, so we probably had a little audio mix up there. I had a typo down the road and I had to rewind, so to speak. Let's get caught back up real quick here. So we've got 72 minus 64, that's 8, minus 8, so that's 0. And so what we're left with is 36 minus 64h, which would be negative 28h minus 16h squared over h. And I've got a common factor of h in the numerator. So it's negative 28 minus 16h. And then the cancellation property allows me to do this. And so that limit, I do direct evaluation now because it's just a polynomial, is negative 28. So the velocity after 2 seconds is negative 28 feet per second. Which just means that if it's negative, that it's coming back down. So it's falling back to Earth. Okay, so we did the calculation here in a different way. We used this formula for the derivative. Again, they are equivalent. We'll have plenty more examples where you can see this worked out. It's a little bit cramped on the slides, but just wanted to show you something along with the general information. Okay, so to wrap things up, we've looked at tangents and velocity as specific examples, but we want to remember the general case, and this is the big idea. Derivatives describe the instantaneous rate of change of a function. So it could be, it could be velocity as a rate of change of position. It can be all sorts of things, but that's the key idea. And this is our first big calculus concept. It's describing the rate of change of a function, instantaneous rate of change. And again, all this works because of limits. That's why we spent so much time working on limits. Limits make calculus work. So early on, these calculations are going to be not super fun because the limit stuff is pretty messy, as we saw. But once we get a handle on what it is we're looking at, we're going to learn a lot of tools and tricks and properties in order to make these calculations a lot faster.